More when I will be in Doha.
We can discuss more. Yeah, definitely. Again, Professor Indigo, thank you very much for very interesting talk, and we really appreciate for your time and for giving this presentation. Thank you very much.
Thank you. Thank you for the invitation.
Yeah. Now we will move to the next talk. The next speaker is Professor Sean, Professor Ho Sean from the University of Technology, Sydney. Professor Sean there, okay. So Professor Sean is the director of the Australian Research Council Research Hub for Nutrients in the Circular Economy and Deputy Director and founding member of Centre for Technology in Water and Wastewater at the University of Technology, Sydney. His research interests include resource recovery, membrane technologies, water treatment processes for water reuse and desalination, and environmental nanomaterials, physicochemical processes, and environmental application. He is externally engaged as the president of Membrane Society of Australasia and editor for the Journal of Desalination. The title of his talk is Nutrients in the Circular Economy. Welcome, Professor Sean. The floor is yours. Thank you very much for giving the talk to this interesting workshop.
Thank you, Professor Jai. Can you hear me clearly?
Yes.
Okay, that's great. Thank you for this opportunity, Professor Shane Han. I'd like to thank you, everybody. I'm very happy to see Professor Enrico Drolli, and then Professor Yuan Chen, and then Professor Ephraim, and then all our friends, and good to have this kind of webinar. And today my talk is about nutrients in a circular economy. I just have this contents, just briefly introduce our group activity, and then just the concept of the definition of a circular economy and resource recovery, because today's topic is very much important, resource recovery and circular economy. So just want to make it clear what's the definition of these two terms. And nutrient in a circular economy, we very much focus on this time of the urine. What's the challenge and opportunity for this urine nutrient recovery and resource recovery? What's the gap to reach the marketable urine treatment technology and technology developed so far from our university and Europe, and as well as the US, also China and Asian country. And then recently we have received the ARC Research Hub in a nutrient circular economy hub, so that we just briefly introduced what we are planning to do for next 5 years, and then a little bit of also important key point of socio-technical and institutional issues, and then lastly take-home messages. So this is one of our activity. Also Professor Drolli mentioned about membrane importance. Also we have contributed our research on membrane fabrication in terms of the membrane distillation, also hollow fiber, microfiltration, ultrafiltration, photosmosis, ion exchange membrane, especially for CDI, and then organic solvent nanofiltration. So MJ Park and Nashat and Ms. Chen Wang are working on this membrane fabrication area. Also lithium recovery from seawater and then salt lake. Also Professor Drolli mentioned about resource recovery for lithium recovery in seawater. Especially our group very much interested in CDI, lithium selective ion membrane development. So we have applied for the CDI and the ion exchange membrane for the recovery of the lithium. So we are contributing together with Dr. Nashat Akhar and Said Hussein and Ms. Hanwei Yu. And this is our applied research. So we also, based on our previous CDI experience, So we have funding from the United Nations. So there is one very small country, capital is the Funafuti. So Tuvalu, they are very much impacted for the sea level rise, so that they have a little bit of salt contaminated groundwater. So we have collaborated with them to look at the renewable energy, solar driven, the CDI, desalination technology, to have more applications. So we have now working to apply our develop solar power, the CDI technology in Tuvalu for desalination. So Dr. Sharul Puncho and Pema working on this area, and MJ Park and then Ms. Chen Wang, they are working on the organic solvent nanofiltration. Austria, we have legal of cannabis. So cannabis includes CBD and TMC, which is the medical application. So there are a lot of organic solvent utilization. So we want to contribute this organic solvent, how to recover using the organic solvent nanofiltration to separate some of the specific compound in the cannabis, so that we can save a lot of energy, also safety concern, rather than distillation process. That's our overall research activity. And today, my main topic is about the circular economy and resource recovery. So let me tell you what's the definition of circular economy and resource recovery. So a circular economy is an economic system that tackles global change like climate change, biodiversity loss, and waste and pollution. Resource recovery is using waste as input material to create valuable products as new output. So if you look at this diagram, so you will have a better understanding. So resource recovery is more about how we can make a less natural resource using our recovered resource, and then we design for the circular economy and manufacture for circular economy. So this is more about the manufacturing side. So the resource recovery is a subset of a circular economy. So the circular economy is more about the bigger concept of the resource recovery. So today we want to recover urine to fertilizer. That's my talk. So as soon as you get up in the morning, so what you are doing for the first time, so somebody drink water. Most of people, they have to go toilet. So when you urinate, so what's your urine inside? So you can see a lot of nutrients. Water is very high content, and nitrogen, phosphorus, potassium, calcium, magnesium, sulfate, iron, manganese, boron, molybdenum, zinc, copper, and then some of the organics, also some of the micropollutants such as pharmaceuticals or hormone, as well as sodium chloride, some of the pathogens because of the outside contamination. So we produce the urine every day, almost 1.5 liter from each person. So there are a lot of concentration of nutrients. If we recover, so we can produce a lot of fertilizer as a good material without any risk problem. So this is what we live for today. So we are very much a linear economy. So we produce the nitrogen from the Haber-Bosch process, nitrogen fixation. So we produce the urea or ammonia and to supply to food. And this is the phosphorus, which is the very limited reserve. And then next to 50 years to 100 years, the phosphorus demand will be very much required, and then there is no replacement of the phosphorus. So we have to make sure recycle and then circular economy system of phosphorus. And we produce the food and we consume in the city. While we are consume, we produce the CO2 and then some of the nitrogen oxide, which are very much greenhouse emission material. Also some of them leaching and runoff and goes to the waterway through after wastewater treatment plant to discharge nitrogen and phosphorus. So we don't really utilize it as a circular economy system. So that my study is about how do we make this linear economy to a circular economy system. That's our research about. If you look at the international fertilizer, world is US around $150 billion, and we have to keep increasing because of the increasing population and industry. Also global shortage of the nitrogen and phosphorus fertilizer, so that it will be more and the price will be higher. So if we potentially cover our urine to fertilizer, so we can cover a large portion of total market, and of liquid fertilizer market can be recovered. So let's say now in 2021 we have 7 billion population, and then everybody produced 1.5 liter per day, so that we produced 12 billion liter of urine. So 12 billion liter urine contain around 20 gram per liter of the salt, which are mostly fertilizer, and then we can convert to our fertilizer. So we produce every day 240,000 ton of fertilizer, and this is especially nitrogen, because this is the highest concentration. 4,800 nitrogen ton per day we can produce. So 1 ton of the nitrogen, which almost $3,000. So every day we can convert this fertilizer to the dollar value. So we produced almost $17 million of fertilizer price. So 7.9 billion population we recover fully for our urine to fertilizer. So we can get the $17 million of the fertilizer, as well as some of the environmental economic impact will be much higher than what we expected. So if you look at the urine, we just discharged to the wastewater. Wastewater urine content is less than 1%. But if you look at the urine nitrogen concentration is almost 6 gram per liter, phosphorus 300 gram per liter, and micropollutant is about 100 microgram per liter. So they contain almost 80% in a wastewater. So phosphorus 65%, micropollutant 50%. So if we try to make a source separate urine, this will be much more effective to treat the wastewater to remove the nitrogen, phosphorus, micropollutant, as well as we can create the more concentrated fertilizer. So that's the reason why we want to develop the more effective technology. Urine diversion can enhance food security by recovering nitrogen, phosphorus, as I mentioned, also reduce the energy associated with the fertilizer production and nutrient removal. The Haber-Bosch process consumed 2.5% of the world energy consumption, because of the you need almost 1,000 Celsius degree of the temperature to make sure that your nitrogen fixation from air. And then in a wastewater treatment plant, so you have to do nitrification, which required a very high aeration. So aeration, you need 60% of the your energy consumption in a wastewater treatment plant, so that you can save a lot of energy, because we separate the nitrogen from our urine diversion system. Also, we can reduce the water consumption by reducing flushing and improve the water quality. So that's the main key point, so that we can try to make a linear circular economy to a circular economy system to produce our food, and then collect nitrogen, phosphorus to produce fertilizer and grow food. So that's the way we can make sure that our economic growth, as well as this environmental protection. So let's look at internationally who are working on urine diversion system. So there are several countries already. They have developed a lot of new technology and then effective way of the process. So Swiss group, their building has urine diversion system. Sweden and some of the U.S. country in Seattle, as well as the Michigan Beach Earth Institute. They are very much working on the urine diversion system, and this is the very latest urine diversion toilet. So you can see that this is the very traditional way. You can see the hole at the front of the urine diverting toilet. So you collect urine from here, which your feces goes to the behind. And this is the latest version of the smarter toilet. So you can see the urine comes to the front part, and then because of the surface tension, the urine comes to the urine diversion plumbing system, as well as we have feces at the behind, and then we can just separate urine and feces so that we can easily divert our urine with the feces. So if you look at the urine aging, so when you urinate for the first time, most of people, they can see this color, yellowish color, because this is some of the organics created your urine color is yellowish. Mostly very high concentration of urea. Urea is almost 2% of your fresh urine. So as time goes by, the urine just change to the brownish color, because yellow color mostly some of the organic, such as phenol. Phenol is contact with the light, and then they convert to the some of the change of your phenol molecule, and then they can change to the some linear structure and then produce some kind of brownish color. So you can think about apple. You know, when you have one bite of apple, so initially it was a little bit white, and then after 1 hour later, so because of your saliva and then some of enzyme, as well as some oxidation of your air, can change your phenol compounds to linear compounds, so that the apple changed the brownish color at the surface. So this is very much similar organic effect as well as the aeration effect. They have a change of color, and then you can put the urea there, which is the hydrolysis. You produce your urea to ammonia, and then some of the ammonia you created a very high pH. So you increase the pH, and then from fresh urine pH is 6, and then increase the pH 9, and then what happens is that you have magnesium, calcium in your urine combined with the ammonia and phosphate, as well as the sulfate and phosphate carbonate. So you can see some of the precipitate as time goes because of hydrolysis of urine. So you produce the calcium carbonate, calcium phosphate, and strobite. Some of the crystal can be produced what you have done in your urine. So after that, you have also bacteria growth, so you can see some of the color, and then more precipitation will be created. So how we can make a fertilizer? So which fertilizer is the best? Fresh urine or aging urine or some hydrolyzed or some of the bacteria fermented urine? Which urine can make best fertilizer for our replacement of the circular economy of the nutrient? That's exactly we have studied for last couple of years. So already this is the marketable urine technology. Strobite can be combined, magnesium, ammonium phosphate to produce this kind of strobite, and nitrification can make a liquid fertilizer, and ammonia stripping to make ammonium sulfate of the fertilizer. So this is still everybody tried to commercialize, but it's not yet fully commercialized because of the cost effect. Still, the technology and then process, also public perception, there are a lot of obstacles to make this kind of technology in the market, so that we try to contribute this technology for making the real application of fertilizer commercialization. So we have investigated for last 5 years. So our PhD student Federico Bolpin, so he has investigated some of the urine fertilizer production, so to produce the water recovery and then nutrient recovery and energy recovery. So we look at how we can apply the space application for urine diversion system, and the hydrolyzed urine, how we can produce the good fertilizer, diluted fertilizer, and then how we can produce the power using RED system, because hydrolyzed urine has almost 20 gram per liter, 30 gram per liter of the total dissolved solid, which has a very high concentration of salt. Also, algae can be grown from this technology, so biomass dewatering system can be applied. So we have published depending on our interesting topic. So I don't want to cover all our research, just want to share the most important findings.
Professor, you have 5 minutes.
Yeah.
You have 5 minutes.
All right. So this is our membrane bioreactor and then MD. So we have tried to convert our urea to fertilizer, nitrification, and then concentrate to produce our fertilizer. So this is our university. We have a 15th story of the building. So we have a urine diverting toilet. So we just collect our urine at the basement of our building, and then we go through the nitrification to remove the smell, and then convert the ammonia to nitrate, and then concentrate and produce our concentrate fertilizer to grow some food. So lettuce and pak choy, as well as some of the parsley we have tested, and then this is our performance data of the membrane bioreactor. So you can see what's the initial urine, concentrate urine, and then this is the permeate of our concentrate urine. So this is the permeate, and then our concentrate urine concentration, and then low urine. So you can see the ammonia and phosphate as well as potassium, which are the major nutrients. So when you have concentration of your ammonia, so we have almost 30 gram per liter and 29 gram per liter, almost 50 gram per liter, and potassium is almost 5 gram per liter, and potassium is 18 gram per liter of concentration. So we have tested this hydroponic system, and this is the comparison of our fertilizer and the commercial fertilizer, and we found out very much similar performance. So we have developed this membrane bioreactor and membrane distillation to concentrate our fertilizer. So we have operate for our lab scale and pilot scale our concentrated fertilizer for last 1 year to produce our fertilizer. Also, this is the very simple hydroponic system to grow coriander and basil. So we found out the commercial fertilizer and our fertilizer, and very much similar performance. Also, we have working on some of the also group in our project. So they have developed electrodialysis to concentrate our fertilizer. So this is hydrolyzed, contained ammonium, potassium, and then this is a cation ion exchange membrane. So pass through your ammonia and potassium, sodium, as well as you have this channel to come to your anion compound like a phosphate and carbonate, come to your anion exchange membrane to concentrate further your fertilizer. So we have tested this fertilizer, and then they are very much also very high concentration of this fertilizer. And this is the micropollutant, our trial. So we found out that some of the micropollutant can be detected from our urine, and then we tried to utilize the activated carbon, and then we found out that most of micropollutant can be removed from the activated carbon. So we combined this system. So based on that, we have developed our research for the hub to look at the more urine collection, processing, optimization, and the user. So that's our project overall aim. So we have 20 organizations who are working on the different research theme to develop their own expertise of the technology. So that's the economic benefit. If we have this urine diversion, you can reduce 30% of the energy cost in a wastewater treatment plant, 60% reduction in energy cost when you have more stringent nitrogen concentration. Also, you can reduce the 40% of the greenhouse gas emission and 50% of fresh water use. You can reduce the 45% in eutrophication potential because you recover the high concentration of nitrogen and phosphorus. So that's what we are trying to look at, the different application of this urine recovery system in the building level, as well as anaerobic digester and animal wastewater which contain very high concentration of urine. Also public toilet together with the green wall, and then some of the vertical farming system can be combined, this technology. And also we look at some of the transdisciplinary research angle, and this is I don't want to make a very detailed presentation. So this is the last slide. So I want you to have a take-home message from this presentation. So we have more importance of a circular economy and resource recovery. And urine is liquid gold, and we can recover. Urine diversion can do a lot of things: food security, energy reduction, water reduction as well. Also, urine diversion can benefit climate change, circular economy, nutrient resource recovery, nutrification, and wastewater infrastructure. And we need to look at also social, technical, environmental, economic, and political issues to make this process, concept happen to our market. Also public education, public feedback, and public advocacy will be our also next step to further develop this technology. And I'd like to thank you again to Shane and Professor Zahid to invite this interesting webinar. Thank you.
Okay, thank you very much, Professor Sean. Very, very, very interesting. And now I think, as you said, urine is the liquid gold, so I think people will not urinate. We will be careful, and they will preserve the urine.
Absolutely.
Thank you very much for a very interesting talk about the nutrient recovery. We can take one question if there is somebody. Say here. Okay, please go ahead.
Actually, I'm actually waiting for my talk, but this is very, very fantastic work. So, how much it costs to kind of convert a regular toilet with connection and the transport? Is that reasonable within a reasonable accepted level, which people are willing to do such additional construction work for their facility?
That's exactly a very good question, Professor Chen, because alleged economic analysis is very much important. So we are also one of the key objectives to look at the cost benefit of this technology. We believe that we have a building level, or also we have a more urban level of the urine diversion toilet can make more urine, so that we can make a process of this urine and then create the peri-urban agriculture sector. Let's say 100 kilometer or 200 kilometer, we can try to supply our concentrate urine to farmers and growers. So that's the cost effective. We found out return on investment based on our simulation is 5 years. You can recover all your investment based on the fertilizer price as well as the energy production saving cost. So overall, nowadays also a lot of indoor farming, a lot of urban farming, a lot of greenhouse system in Sydney and also around the world, they have a lot of parks in the city. So you can connect easily from building or some of the public toilet, and then you collect urine easily and then convert your urine to fertilizer and apply it to your parks, and then some of your green wall indoor farming system. So that's the way also we can save a lot of transportation cost. So that's the way we have to think about how we can make more economically viable this technology to have more opportunity. So it's correct. Some places may not be economic, but that's exactly our project we are planning to develop through this AIC NICE Hub, how we can apply to cost-effective way of this nutrient in a circular economy system.
Okay,
Thank you.
thank you very much.
Fantastic.
Yeah.
Thank you.
Can I make a
Okay,
comment?
now, since we need to catch the time, so thank you again, Professor Sean, for your interesting presentation and giving some idea and just to how to preserve your waste and to recover this useful product from our municipal waste. Thank you very much again.
Thank you.
Now we will move to the next presentation.